All right, sum and difference identities. So they give you this whole long proof on page 336, which is great, but honestly, memorize it. Okay, memorize the formulas. Don't try to prove it, just memorize it. All right. These are called sum and difference identities because obviously you're adding two angles. Alpha and beta are just two angles. And so there are going to be times when the sum of the angles you don't know, but you know the individual ones. So if you were to add two angles on the unit circle, you could potentially get an angle that is not one that you have memorized on the unit circle, and you can split it up into ones that you know. These identities help you. So memorize them. Cosine, the sum and difference identities for cosine. It's cosine of the two angles minus sine of the two angles. You'll notice the sign here positive, and the one here is negative. This is how you're going to remember this one. It's cosine, cosine, sine, sine, and it's opposite. So the subtraction is going to be cosine, cosine, sine, sine, and it's the same. Like opposite here, right? Opposite for both of these. Look at sine. Sine is sine, cosine, and because it's multiplication, it's sine, cosine. Doesn't matter. But the addition is the same here. Sine, cosine, cosine, sine. Subtraction, right? And then tangent. For adding, you're going to add the tangents of the individuals and then 1 minus the multiplication of the tangents. All right, so the addition sign matches the numerator. All right, the subtraction sign matches the numerator. Subtract the first one minus the second one, then add the sum of them. All right, and so you need to memorize these so that you know how to use them. So we're going to actually put them into practice. Look at example 1. Find the exact value of each trigonometric expression, all right? So this first one is 15 degrees. 15 degrees is not one of your common angles on your unit circle, all right? And so we want to use two angles that are common angles on our unit circle and either add or subtract to get 15. So what are two common angles they'd either add or subtract to get 15? By common, I'm looking for like 30, 45, 60, or any of those measurements around the unit circle. 45 minus 30. So I can rewrite this one to be the sine of 45 degrees minus 30 degrees. Does everybody see that? And now I can use my difference identity here of sine to solve this. So I can say the sine of the first one times the cosine of the second one. And it's subtraction with sine, so I'm going to also use subtraction, minus the cosine of the first one times the sine of the second one. All right? Literally just plug it into the formula. Now this next part is using your unit circle. All right? So what is the sine of a 45-degree angle? Square root of 2 over 2. What's the cosine of a 30-degree angle? Cosine of a 45. And then sine of a 30. Okay? So I'm just filling it in. And then I'm just going to simplify. Square root of 2 times square root of 3 is the square root of 6. 2 times 2 is, of course, 4. Square root of 2 times 1 is the square root of 2. We cannot simplify those radicals because they are not like radicals. So my final answer here is going to look like this. So the way they do this one is 7 pi over 12 is they look for what makes a 12 as far as the denominator. So you do not have a 12 denominator anywhere on your unit circle. You have 3 and 4. And so you can say, well, what angle with a base 3 and then angle with a base 4 would give me 7 pi over 12? You can, 7 is easy. That's going to be 3 and 4. Okay. However, that is not how this always is. So really, there's an easier way to do this. You can actually just convert this to degrees and then just use degrees, right? Because if not, you're going to have to be trying to calculate your denominators. And I really, like 7 is an easy one because it's pi over 3 and pi over 4. And so you get common denominator 3 pi over 12, 4 pi over 12, and you get 7 pi over 12. And so that's simple. When you throw crazy ones out there that don't do that quite as nicely, it gets a little more difficult. And so it might be easier just to convert this to degrees. So either way, I'm going to use tangent. And I'll show you this way first, and then I'll walk you through converting it. So tangent of pi over 3 plus pi over 4 is going to give you 7 pi over 12. If I get a common denominator of 12, multiply the 3 times the 4 times the 3, I would get 7. All right? If you convert it, how do I convert 7 pi over 12 to degrees?
7 pi times 180 over pi.
180 over pi. All right? So I'm going to simplify this, right? What goes into these?
12.
And what's left over here? I'm going to go with 15. Okay. All right, 7 times 15 is 70 plus 35, 105 degrees. All right. You can distribute 7 times 10 plus 7 times 5. All right, so 105 degrees. So then you could do two angles that add up to 105. All right. And that might be a little bit easier. So I could also say the tangent of something like 60 and 45 degrees, which is what those two are. All right. But figuring out that common denominator sometimes stumps people. So either do it by radians or degrees. I don't care. Your final answer is going to be the same. All right. You just may be able to visually see the degrees better than the radians. All right. And so if we actually take my tangent says that I am going to do, if I have a tangent sum, I'm going to do the tangent of the first one plus the tangent of the second one over, this is a sum, so it's 1 minus on the bottom, tangent of the first one times tangent of the second one. All right, and then we have to do our tangents. What's the tangent of a 60-degree angle? Sine over cosine of a 60-degree angle. Yeah, it's square root of 3 over 2 over 1/2, right? Which is just square root of 3. Plus tangent of 45, that's easy. 45s have the same sine and cosine, so it's 1. All right, and we've already calculated this, so we have 1 minus the square root of 3 times 1. So I end up with the square root of 3 plus 1 over 1 minus the square root of 3. And they rationalize this, by the way, because there's a root in the denominator. So they took this guy and they rationalized it. So we do, remember how we rationalize 1 plus the square root of 3, 1 plus the square root of 3. Foil the top. We're going to get the square root of 3 plus 3 plus 1 plus the square root of 3. 1 minus 3 on bottom. So you end up with, I'm going to scoot this over a little bit. Simplifying it, you end up with 4 plus 2 square root of 3 over negative 2. So you end up with negative 2 minus 1 square root of 3. So an alternating current I in amps is in a certain circuit can be found after t seconds using I equals 3 sine of 165t. And I think in your book you have parentheses around your sine of 165 maybe? Okay. It will not make a difference because they use t of 1 second. But just FYI, mine looks different. So the difference is that it is the 165t, it might affect, if it were not 1, might affect what two angles you add up to get it. So, but it would be distributed anyway, so I don't think it's going to matter that there is a parentheses around it. All right, so they want us to solve for using sum of two angles. And so with 165, that is not on our unit circle. So we have to find two angles that add up to it. And so what two angles on the unit circle are going to add up to 165? Yeah, 120 and 45, right? So we're going to have the sine of, and yours has the t on the outside, right? So it's going to look like this. I think for yours, mine looks a little bit different. This is after 1 second, right? It specifically says, rewrite the formula and sum of two angles. And then after 1 second is the second part of this. So if I plug in a 1 here for my t, then I'm just going to be solving this piece of it. Sine of 120 plus 45. All right. And so then we're just going to plug it in. 3 is going to go on the outside here. All right. And we're going to say, using our sum identity for sine, we're going to say the sine of 120 cosine of 45 plus cosine of 120 sine of 45. All right. So sine of 120. What quadrant am I in? I'm in the second quadrant, right? So I have to consider that when I do my sine and cosine. My sine is still positive, but in the second quadrant, what is my cosine? Negative. So for 120, the sine of 120 is what? This is a sine of a 60-degree angle, right? Square root of 3 over 2, right? Cosine of a 45-degree angle. Plus the cosine of a 120. Negative 1/2. And then sine of 45 is square root of 2 over 2. So when you have these angles, you do have to consider what quadrant you're in with your positives and negatives. Same thing as you would have to do always. So we have 3 times the square root of 6 minus the square root of 2 over 4. And I think they just distributed that. So 3 square root of 6 minus 3 square root of 2 over 4. So in this case, they have given us these angles that we do not have on our unit circle. And at this point, you might actually recognize that this is your tangent formula for sum, right? And so you can rewrite this as the tangent of 1 because you recognize, well, this is tangent of A plus tangent of B minus over 1 minus tangent of A, tangent of B, pretty much. And so this is going to be the tangent of the A plus the B, which is the tangent of 45, which is 1. So if you recognize that you have a sum or difference, you can actually condense them as well. It's like we've been expanding them. We've been given an angle and we've been expanding it into two different angles. In this case, we've been given two angles and we're condensing it using our formula here. Let's look at this next one. So for this one, we have sine, sine minus cosine, cosine. That is not one of our formulas, but it's very close. What is it close to? It's similar to cosine, but it's not exact. Now let's say if I pull out a negative 1, then I will get a positive cosine, cosine, right? Positive cosine x, cosine 3x, and I would get a negative sine x, sine of 3x. Now this actually looks just like my cosine. Which one, addition or subtraction? What does the inside look like there?
Cosine of A plus B.
A plus b. So this is going to be negative 1 times the cosine of a plus b, right? Which is negative cosine of the sum of them. So we did verifying in sections 1 and 2, and they're just showing you how this came to be. So if you remember your cofunction identities, the sine of pi over 2 minus an angle is the same thing as the cosine of that angle. That was one of your cofunction identities. And so this is just showing you the proof of that. The proof of this lies in your sum and difference identities. Because my sum identity here says, or my difference identity says, that would be the sine of pi over 2 cosine of x minus the cosine of pi over 2 times the sine of x. All right? And we can fill those in. The sine of pi over 2 is just 1 times the cosine of x. The cosine of pi over 2 is 0 times the sine of x, so you end up with just the cosine of x. And you can see that that actually works, right? And so for an identity that we memorized earlier, you can see why it works with your sum and difference. The same is true, which I don't think we've done the reduction identities yet, but even the cofunction identities with degrees is the same thing. So example 6 is really kind of the same idea. So just verifying some of these identities that you are memorizing, they stem from your sum and difference identities. That's where they come from. All right? So let's jump to example 7, which is solving. So it says find the solutions of the cosine of pi over 3 plus x plus the cosine of pi over 3 minus x equals 1/2 on the interval 0 to pi. So we're not just simplifying these, we're actually solving for an angle is what we're going to do. And so we're going to use our sum and difference identities here to do this. My cosine sum. So my cosine sum says the cosine of the first times the cosine of the second minus the sine of the first sine of the second. So that's what I can replace this part with. And then I'm going to add to it my difference, cosine of the first, cosine of the second, plus sine of the first, sine of the second. And that's what I can replace this one with. All right. And so what actually happens here is I end up with two of these, right? So I have cosine of pi over 3, cosine of x, cosine of pi over 3, cosine of x, right? And so I end up with two of those, 2 cosine of pi over 3, cosine of x. And then for my sines, my sine values here, negative sine of pi over 3 sine of x, positive sine of pi over 3 sine of x, those cancel out. So these actually cancel out completely. And I'm left with what it equals. It equals 1/2. All right, it equals 1/2. Now, I actually can fill this in. Cosine of pi over 3, that's an actual number. What is the cosine of pi over 3?
In degrees?
In numbers. Cosine of pi over 3. Pi over 3 is an angle. What's the cosine of pi over 3? It's the cosine of a 60-degree angle. It's 1/2. So I have 2 times 1/2 times the cosine of x. What happens here? 2 and 1/2 become 1. So I just have the cosine of x equals 1/2. I want it on 1 unit circle. Where does the cosine of x equal positive 1/2? There are 2 places on the unit circle where this happens. We just found one of them. That happens at pi over 3. And it happens in the 4th quadrant as well.
Just negative 1/2 or just
No, positive 1/2.
5 pi over 6?
5 pi over 3 for cosine x value. All right, so we're going to use our cosine sum, which is the cosine of the first, cosine of the second, minus sine of the first, sine of the second. Then we're going to subtract my sine, which is sine cosine minus cosine sine. And all of that equals 0. Okay. And so we're going to fill in what we know. My cosine of pi is -1. My sine of pi is 0. So we're going to fill that in. All right. And so we end up with, over here, we end up with the negative cosine of x. This zeroes out. And then plus the sine of x. And that zeroes out, and that equals 1. And so if I set those on either side of each other, sine of x equals cosine of x, there are 2 times on my unit circle where my sine and cosine are exactly the same. Where is it? Yeah, at pi over 4, we get square root of 2 over 2, square root of 2 over 2. And then in the 3rd quadrant, at my 45, at 5 pi over 4, we get negative square root of 2, negative square root of 2. Okay? The other way to look at it is if I were to divide both sides by cosine, where does my tangent equal 1? So 2 places on the unit circle where cosine and sine are identical.